Now we have Murali, who is going to talk to us about load balancing.
Okay, can everyone hear me? Yes, I can hear my own voice. Excellent. Good afternoon, everyone. My name is Murali Suriar, and this is a talk that a colleague and I, Laura Nolan, put together. I literally just tested this thing. Why is it now not? Okay, fine. I'm not using the clicker. This is a talk that a colleague and I put together primarily because there is very little reference material for how to do kind of integrated load balancing up and down the stack. There are plenty of things that tell you this is how you do network load balancing, or this is how you do high availability, how you do DNS load balancing, or how you do high availability web servers. There's very little talking about how to do top to bottom stuff that is modern. The last one I'm aware of is Theo Schloss-Nagel's book from like the early 2000s. I am a computer scientist turned network engineer turned network SRE. SRE is Google's take on how to do operations with software. I now work in storage, but I spent about 8 years doing networky things. Laura went the other way, so she started off as a software engineer, then became a non-networking SRE, and then joined networking later. So why are we talking about load balancing? Load balancing failures turn into dropped requests, right? The short version of this is that I suspect many other people in this room have spent a lot of time debugging things that turned out to be networking load balancing failures. The goal here is to start with a very simple topology and then layer existing sets of load balancing technologies on top of that to get to the point where we're describing what could be a fairly large, highly scalable architecture. This is not a, this is how you should do load balancing talk. This is a, here are all the tools available to you and how they interact and what you should think about when you are choosing which of those tools to use. Just because we needed to pick either the top or the bottom of the stack to start with, we're going to start with kind of a network-focused view and then move our way up. So we'll start with a very simple web app, right? It's a static content service just serving photos of owls, right? The highest quality owls you've ever seen on the internet. For those of you who aren't aware, this is an actual Reddit. It's great during the Super Bowl because there are lots of very confused people trying to work out why there are pictures of owls. But yeah, we'll start with a web app, and we'll start with a single server, a single machine. We're going to hand wave over how you scale your application, right? There are many good references on that. If you want a recommendation from me, Martin Kleppmann's Designing Data-Intensive Applications, I forget the exact title, but Martin Kleppmann, Data-Intensive Applications is like a fantastic book. So your customer, who is a vendor of owl-related products, is setting up their first website, superbowls.com. This is where we're starting. And so the 99 times out of 100, what this will end up looking like is you will have a server in a rack somewhere. You will assign a public IP address. We're using IPv4 just because laziness. An IPv4 address to that server, 2030.113.20. Your colo provider or your internet service provider's edge routers are advertising a prefix containing that IP address to the internet via BGP. And you have a DNS provider somewhere and who is responsible, who's authoritative for superbowls.com, and you tell them to serve up an A record for that name, which points to the address of your server. There's basically very little redundancy in this picture, right? If you're lucky, your colo provider will have redundant uplinks to the internet, right? But other than that, we haven't really put any kind of high availability in here at all. And it's very hard to scale this, right? Your only scaling dimensions are what is the size of the link between your server and your colo provider? Like maybe it's 1 gig, then it moves to 10 gig, then it moves to 40 gig. And the other thing is how big is your server? And those are the only two things that you can fiddle with in this scenario. It doesn't have load distribution, right? Like there's one web server, we can't serve any more traffic than it can handle, so you can keep throwing money at whoever your hardware vendor is, but that's it. you don't have any high availability really, right? Like if your machine goes down or if any of those components goes down, you are basically, your customer is down. They cannot serve their customers. There is some amount of load distribution though, right? Like network engineers just kind of do redundancy by definition, just architecturally. You'll end up with redundant paths across the internet or even redundant paths between 2 points in a single data center. So the network piece of this, and we're mostly going to hand wave over it, we'll talk about it in a little bit of detail, can be transparently increased in size, mostly transparently to the user. And similarly, this is true on the public internet as well, right? There are many redundant paths through the public internet. So the problem here is we have some high availability, but it's mostly outside of our control, right? It's in the control of our ISP or in our colo provider. And you have things like what happens if you have a flaky link inside your data center, right? Let's say the link between your server and your colo provider is flaky. Is that your problem? Is that your colo provider's problem? What can you even do about it if you only have the one link? So we'll add, the first thing you're going to do probably is you're going to do a single, add a second server, right? Let's say for whatever reason, we have chosen Raspberry Pis as our hardware platform because we've all gone to LCA and we've got a free one. And so our Raspberry Pi, I don't know what a Raspberry Pi can serve, how many OWL pictures it can serve, but let's say it can serve 5 OWL pictures a second, right? And so if we only have one of them, 5 concurrent requests a second is the most we can serve. So maybe we want to do 10 requests a second. And so if we have greater than 5, we need to add another unit of increment, right? And that's a step function up. This is not a capacity planning talk either, so that's yet another talk, so we'll just kind of ignore how you come up with these numbers. So in our existing setup, the way we would add another server is we would add another server, it would get another IP address. Probably it's from within the same network block that our existing server is in. That's not guaranteed. And we would probably add that second IP address to the DNS records for our services name. And that will, depending on a multitude of things, there are several people here who I suspect are interested in the DNS, but like DNS client library behavior, stub resolver behavior, recursive resolver behavior, like many different things can influence whether an end user sees 2 IP addresses or just one, what order are they returned in. But let's assume all of this works as spec'd and as designed, and you have large enough amounts of load, you will probably end up with about half of your load going between each of your servers. And this is fine, except when a server goes away. So when a server goes away, what happens? About half of your clients will see timeouts, right? So they will get, let's say they get both IP addresses back and you're relying on the client to pick between them, and they pick randomly. Half of your clients will get timeouts. Someone will probably tweet at you unless you have monitoring, and then you'll know before someone tweets at you. So then the way you fix this is you change your DNS configuration, right? So what we've done here is we've taken .21 is the server that's died. We've taken .21 out of the DNS records on the left-hand side. And eventually, after a TTL, after a time to live, your users will be happy again. We'll talk about TTLs in a bit shortly. Some clients maybe are smart about this, right? Depending on the client software you're using, the client software may say, oh, I've got 2 endpoints to connect to, but one of them's dead, so I'll just prefer the other one. But if this is just a browser, right, there could be people using like Android Froyo or whatever who are trying to access your website. Like, it's by no means guaranteed that these clients will be what I would consider well-behaved. So yeah, TTL trade-offs. There are 2 dimensions here, right? You can either have super, super long TTLs or you can have very short TTLs. Very few people do anything in the middle, right? And when I say super long, I'm talking like a day or multiple days. When I'm saying short, order of 10 seconds to 5 minutes, right? Like, I'd be interested to know what the actual distribution is for names on the internet, but I suspect that people do one or the other. If you have long TTLs, then your users will not see any change you make for a significant period of time, right? Like 86400 or 84600, whichever way around it is a number that many people know if they've configured DNS zone files. If you have that number set, then any change you make will take at least 1 day, probably longer, for it to be visible to all of your users. Conversely, with very short times to live, this means there will be much higher load on your DNS infrastructure, right? Because let's say you say this DNS response is only valid for 5 minutes, then we end up with significantly more load on the DNS with the benefit that it means that changes we make to the DNS are more quickly visible to your customers, to the endpoints that you're trying to direct to your service. Clients have to query the DNS more often, which adds latency, and various DNS implementations maybe have weird timeout bugs and whatever, and that could add like significant amounts of user visible latency. The other big thing to bear in mind is the lower your TTLs are, the higher the proportion of your error budget is consumed by DNS, right? So if you're when you have shorter TTLs, you need much more reliable DNS because it's at any given time or any given request, it's much more likely to be hitting DNS in some form. And the other thing to bear in mind is many DNS client implementations, stub resolvers, and recursive will ignore TTLs below a certain threshold, right? So I don't know what the spec says. I'm going to hand wave 5 minutes rather. I've seen some people use 10 seconds, but again, you have to know what the set of clients you're using is and what they will or will not obey. 5 minutes is like a reasonable rule of thumb for a lower bound on the internet. So back to our story. So our new story now, we have these multiple servers with different public IP addresses. We have a DNS record that points at both of them. We're now doing load distribution, right? We have multiple pieces of serving infrastructure. We don't really have high availability, right? And the other thing, sorry, to bear in mind, I'm saying load distribution here, and the talk's title is about load balancing. The reason I'm saying load distribution is because the DNS has no concept of how loaded or busy any one of these servers is, right? In our current setup, it's just assuming that all queries cost about the same amount in terms of compute resources on your machines. It assumes they all last about the same amount of time. And so you'll get kind of approximately equal load. But if you have a mix of queries, right, like maybe some ALs are very expensive to serve and some ALs are very cheap to serve, then there'll be all sorts of interfering effects here. High availability is not a great story, right? So firstly, you've got propagation delay, which is a function of whatever TTL you've set in the DNS. And the second thing is you don't really have health checking, right? Like if you're running your own DNS infrastructure, most DNS resolvers do not have, or DNS name servers, excuse me, authoritative name servers, do not have the concept of health checking, right? Like if you're running in, I don't know, in say Kubernetes, or maybe you're running in a public cloud, some cloud providers have a DNS product that can health check the health of an instance and remove it from a DNS load balancing group, but this varies very widely depending on what you're using. In terms of flexibility, and when I say flexibility, this is for like humans, operators, or like automation to redirect traffic in response to either failures or for planned maintenance. It's like, but this is going to turn, like, depending on what DNS provider you're using, this could end up being edit a zone file and then like SCP it or post it via an HTTP endpoint and then wait for it to propagate through whatever magic. And it's still going to be quite slow. And to be clear, right, this is not us ripping on the DNS. DNS was not designed for load balancing, right? Like Paul Vixie, like if any of you follow Paul Vixie on public mailing lists, he's like, this is not what it's for. Unfortunately, because it's in everything, people end up using DNS for load balancing because it's the knob they have available. So the next thing here is DNS TTLs are a problem, right? Because even in the case where, where's my failure slide? Even in this case where, let's say we have 5-minute DNS TTLs, serving 50% of errors for 5 minutes is not a great story. Like, it offends me on kind of a fundamental level. So we need a better story for this. And so the next thing people often do is they will add a network load balancer, right? And that's what this black box in the middle here is. So probably it's going to be a cluster of network load balancers. We drew one here because the diagram was going to get busy otherwise, but lots of third-party vendors, or these could be just commodity x86 servers running some open source software. But what you do here is you put the public IP address that's associated with your service website, you put that on your load balancer, and it then is configured to say for requests to this public IP address, here are my 2 possible backends, which are now addressed out of private IP address space. you may or may not put them in private address space, right? Or in IPv6, you'd use maybe non-routable space. It wouldn't be private. Well, maybe it would be private. That gets into philosophical conversations, which best discussed over a beer. But this now gives you the ability to take servers out of rotation, either for maintenance or in response to failure, without any client visible changes, right? Because the configuration is on a device you control. The DNS is back to having a single IP address in the A record, and so you could actually have really long TTLs with this setup, right? Because your high availability is actually not coming at the DNS level, it's coming at the network level. Things to bear in mind, this network load balancer will not know anything about your most of the time, will not know anything about your application layer protocol, right? All it will do is look at the IP header of incoming packets. It will look at, and possibly the TCP header, right? So it'll look at source IP, destination IP, source port, destination port, and then pick whichever backend to use. It also has a ton of state in it, which we'll talk about later. As a former network engineer, state in network devices is the thing I think is a terrible idea. But it does give us a lot more high availability and control over traffic routing, right? Maintaining one of the two individual servers becomes a lot easier. Okay, so now we're going to go off into network LAN for a bit. So we're talking, I talked about network multipathing early on, right? Like the public internet has a lot of multipathing. Your data center provider probably have many redundant paths between machines in their data centers. Mechanically, how does this work? Network devices typically use either what's called 5-tuple or 3-tuple hashing. We'll explain 5-tuple. The process for 3-tuple is the same. So let's say for a given destination, you have n different possible paths you can take. You're on a network device and you want to send to pick 1.2.3.4, whatever, and there are 10 paths you can take. How do you choose? Well, the thing the industry has settled on is you look at the packet and you look at the source IP address, the destination IP address, the protocol, so TCP or UDP or ICMP or whatever, and if it's a protocol that has port numbers, TCP or UDP, you then also look at your source port and your destination port. So that entire bit pattern, you then produce a hash of it. Like network hash functions is a whole other talk, which ones you should use. But based on the output of that hash function for a given 5-tuple, you then pick, you index into your list of backends and pick which one to use. Why do we use the 5-tuple? Primarily because TCP reacts very, very poor, or I should be slightly more careful. TCP used to react very, very poorly to packet reordering. If you send 2 packets from the same TCP flow across different network paths, it is possible, even likely, that they will end up arriving at the far endpoint, possibly in a different order from the order in which they were transmitted. And TCP, if it sees an out-of-order packet, will treat that as analogous to packet loss. And packet loss is what TCP uses to say, oh, there's congestion, let me slow down. And so you want, ideally, all the packets from the same flow to traverse the same set of network links. Other things to bear, and so this diagram below just kind of explains, it shows some example inbound and outbound flows to 2 racks full of servers. A thing to bear in mind as well, just something to keep in the back of your head, basically always, unless you're in a very constrained data center enterprise environment where your network operations, engineering, architecture people have set things up otherwise, basically all the time otherwise, all traffic in the network is asymmetric, which means that the traffic for the same flow in one direction will go over a different set of links when the response traffic goes back, right? Just something to always keep in your head. In terms of, what else do I want to mention here? Hashing. Google's maglev paper is like several years old now, but it explains some of the challenges in picking network hashing. Facebook have a thing called Catan, which is their software network load balancer, which they've open sourced, which implements one of the hashing algorithms described in the Google paper. Okay, so the next thing here is the hash-based algorithm is a very simple one, right? Because it's just like, for this flow, pick this backend. But you can do more interesting things in layer 4 load balancing, right? And when I say layer 4, this is network layer 4, because TCP and UDP transport protocols are considered layer 4. You can do things like least connections, right? So your load balancer, because it's in this setup, in the path of every request, knows how many open connections there are or pending requests there are to each backend. And so you could say, pick the one that has the fewest connections, which for some workloads is actually not an unreasonable thing to do, right? Assuming you never go out of capacity. So this gives us a lot more power now, right? Because we can add more instances to the backend pool, and this is completely transparent to the users, right? There's no DNS change, there's no basically completely arbitrary, right? The only thing that constrains us is space and power and how quickly our physical provider can give us new instances. If you're in the cloud, this is just click a button in the AWS console or the Google Cloud Console or whatever, and it just appears. We can add health checks here as well, right? Because we can say, hey, network load balancer, yes, I know you're only doing packet forwarding, but to establish the health of a server, rather than just pinging it or rather than connecting on a TCP port, hit this particular URL because this is a web server. And if you can serve like Al from winniethepooh.jpg, then this is probably a happy thing, right? So this is much better. It gives us load distribution across multiple pieces of infrastructure. It gives us avoiding unhealthy instances. And it also gives the operators the ability to take individual servers out for maintenance. Usually, the things it doesn't give you knowledge of load on servers, like the differences between different requests, right? Because multiple requests can go over the same TCP connection. It's also not content aware, right? So it's not going to be able to route different requests to different backends because maybe you want your images served from over here, but you want your JavaScript served from over here. And it's hard to do sensible load shedding and denial of service abuse protection because to do that well, you need to typically be aware of application level heuristics and information for fingerprinting. Okay, so we're hiding a lot of network detail. So I'm going to talk fairly quickly because I'm time constrained. All of this stuff where we've said there's a magic network between you and your servers and the internet, we'll talk a bit more about how that works. So your stateless network load distribution, this is just you have many network devices in a path, right? So in this case, let's say you have two edge routers in your data center, and then you have two top-of-rack switches for your racks of servers. 1+1 redundancy is just a very common model in network provisioning. 3+1 or whatever is becoming more common, but historically network vendors have gone scale up rather than scale out, although this is changing. But if we consider one server to and from a rack, you can do something like, so you have two routers. Let's say this server is only connected to the one switch, and then it has two routers connected to that switch. You can do something like VRRP or similar to have high availability at your network gateway level. And at the routing level, you can say one of these two routers, these two circles, is the primary gateway to get to the rest of the internet and receive incoming traffic. Or you can load balance across the two. This is what's called IP multipath. So with this setup, if you have a broken router, then stuff naturally converges via the other path, right? If you have a broken switch, it depends on whether your server is connected to multiple switches or not. If it's only connected to one switch, the server goes away, but maybe, hopefully, you have a redundant server in the other rack. If you have racks full of machines and they're all connected to two switches, how do you make use of all of your bandwidth, right? So this is now, we're talking about a capacity question rather than a high availability question. And the answer to this is something called ECMP, equal cost multipath. This is the thing you'll hear network people throw around. You have many links, they all have the same cost, and you use your different links using the hashing algorithms we described before. Different flows go over different links, and so suddenly your available bandwidth is the sum of all of the available link bandwidth going up or down from a given network device. Typically, this is all stateless, right? This is all done in silicon, and there's no per connection or per flow state in any of these network devices. Yeah, caveats. All flows are asymmetric. The other big thing here is elephant flows are a real problem. Elephant flows are where you have a single flow which is larger than the size of the biggest link you have in a bundle, right? So say your data center provider is using all 10 gig links and you have a flow that is 20 gig, there is no way to solve this problem, right? They will need to upgrade to 40 gig or 100 gig on the physical layer or the link layer to be able to serve that. So yes. So what about soft link failure? With soft link failure, this is generally much harder in the networking world than otherwise, because what this turns into is intermittent packet drops. And often, hardware just lies, right? Like, it will not increment a counter. It will not tell you anything is wrong. And so the only really way to solve this is to have like some sort of external monitoring where you're like trying to spray traffic across as many links as possible and see what stuff has gone down. NetNORAD? Again, Facebook have a thing they've open sourced. I think it's called NetNORAD. I can't remember the name of it, which is doing this kind of introspection. Okay, I'm going to skip over this because proxy this as well. I'm going to skip over. Layer 3 DSR. So we'll talk about these two slides. So with network load balancing, we talked about the proxy setup where all packets inbound and outbound go through the same device. The problem with this is that you are then bandwidth limited by that device, right? So if you have a very asymmetric workload, and in web requests this is typically true unless you're taking a lot of upload traffic, typically your request size is significantly smaller than your response size. And so it would be nice to be able to make use of all of your inbound bandwidth on a single load balancer and have many backends be able to serve. And this is the idea of direct server return. And this is effectively where your incoming packets go through your network load balancer, but your return packets don't. They go directly back out to the internet or to your office users or whatever. We used to do this using Ethernet trickery. I'm going to skip over this. We will make the slides available. People can read after the fact. With layer 3 DSR, the way we solve this is a long set of slides. Which one do I want? I want this one. The short version is load balancer receives an IP packet. It then looks at which backend it wants to send traffic for this flow to, and then it sticks another IP header on the outside of that packet. And what this means is your network load balancer doesn't need to be in the same rack or connected to the same Ethernet switch as any of your backends. And it allows you to still preserve that original IP address information, which is very useful for like spam and abuse and reputation protection and various other things. Skip, skip, skip. So yes, back to our story. So far we've only talked about single data center. If we want to do multiple data center, there are many reasons you might want to do this, right? One is just disaster recovery, right? You don't want an earthquake or a tsunami or whatever to take out all of your serving capacity. But there is also benefit for users, right? Because let's say you're a US-based company. If you have your own data center on the East Coast, your user experience for your West Coast user is going to be terrible. And so if you can have multiple locations, and if you can steer users to those locations, then that will be better. Most of the time when people do this, the first thing they do is they do something called Anycast. This is a whole other rant that I'm not giving a talk about this time. Anycast is hard to monitor, but it is cheap and easy and to do upfront. You basically announce the same address from multiple locations. Users go to the closest one. Yes, it's not load balancing. I gave a whole other talk about this. You can find the slides from SREcon last year, I think. The other option you can do is you can have your multiple data centers have different IP addresses, right? So they have completely independent net blocks, and then you end up with in the DNS configuration, you have 2 IP addresses for a given name. Upsides, downsides here, because if the entire data centers goes away, you still have the DNS TTL problem, right? And you have like 5 minutes or a day before your users are redirected. So the way a lot of people solve this is with something called backup routes or cover routes, where both locations announce both sets of IP prefixes, but each one is primary for one. And so if the other data center goes away, it suddenly starts serving that data center's IP addresses, but it's typically they only serve traffic for their own prefix. DNS geoload balancing, I'm going to skip over this because I think, no, we'll talk about this, I think, and then we'll finish there. So the perils of DNS geoload balancing. So we're talking about here, the idea here is based on the end user's request, you work out where to send them, right? I think this user is approximately on the US West Coast or on the US East Coast, and I will send them to the relevant data center. IP addressing, particularly in IPv4, is very, very fragmented. Secondly, the IP address you see from a DNS request is typically not the end user's IP address, but the address of their recursive resolver. And you may have a large user population behind a recursive resolver who have very different latency profiles to your service, right? Let's say you're an ISP in India, maybe you put all of your users behind a single DNS server, and then their user experience is going to be terrible if that's the only signal you have for load balancing. There is an extension called eDNS client subnet, which allows you to embed information about where your clients are to the upstream authoritative name servers, which gives you a hint as to, I know I'm a DNS server over here in the west coast of the US, but this user is actually coming from Hawaii or whatever, or from the east coast, and you should route them accordingly. This is implemented by a bunch of content delivery networks and by a bunch of DNS providers. I don't think it's actually a standards track standard, but pretty much everyone implements it at this point, or large providers do. I have 1 minute left, so what I'm going to do is I'm going to skip to, where's the thing? Damn it. There we go. When you read these slides, this is what you should take away. Do you care about capacity? Do you care about high availability? Do you care about utilization? How much control do you want over traffic routing? How much telemetry do you want? Do you only care about network level telemetry, or do you care about service level telemetry? Which of those you care about will, in turn, impact which of these technologies you select. There's a whole bunch of stuff at the application layer we haven't talked about. Again, the slide content's fully available. And the other thing here is there is a bunch of reference material which will be on the slides, which people can go and read up on in detail. So I think LCA published the slides on the website, do they? Yeah, so I'll send that through to you and after the fact. And with that, I think I'm done.